Hi guys, welcome to the next section, using reinforcement learning for predictive analytics. Now, we move on to the first video of this section that deals with reinforcement learning. From a technical perspective, whereas supervised and unsupervised learning appears at opposite ends of the spectrum, RL exists somewhere in the middle. It's not supervised learning because the training data comes from the algorithm deciding between exploration and exploitation. And it's not unsupervised because the algorithm receives feedback from the environment. As long as you are in a situation where performing an action in a state produces a reward, you can use reinforcement learning to discover a good sequence of actions to take the maximum expected rewards. The goal of an RL agent will be to maximize the total reward that it receives in the long run. The third main sub-element is the value function. While the rewards determine an immediate desirability of the states, the values indicate the long-term desirability of states, taking into account the states that may follow and the available rewards in these states. The value function is specified with respect to the chosen policy. During the learning phase, an agent tries actions that determine the states with the highest value, because these actions will get the best amount of reward in the long run. The diagram shows a person making decisions to arrive at their destination. Moreover, suppose on your drive from home to work, you always choose the same route. But one day, your curiosity takes over, and you decide to try a different path in hopes for a shorter commute. This dilemma of trying out new routes or sticking to the best-known route is an example of exploration versus exploitation. Reinforcement learning techniques are being used in many areas. Now, let's see notation, policy, and utility in RL. You may notice that reinforcement learning jargon involves anthropomorphizing the algorithm into taking actions in situations to receive rewards. In fact, the algorithm is often referred to as an agent that acts with the environment. You can just think of it like an intelligent hardware agent, sensing with sensors and interacting with the environment using its actuators. Therefore, it shouldn't be a surprise that much of RL theory is applied in robotics. The diagram demonstrates the interplay between states, actions, and rewards. If you start at state S based to 1, you can perform action A based to 1 to obtain a reward. Actions are represented by arrows, and states are represented by circles. A robot performs actions to change between different states. But how does it decide which action to take? Well, it's all about using different or a concrete policy. In reinforcement learning lingo, we call the strategy a policy. The goal of reinforcement learning is to discover a good strategy. One of the most common ways to solve it is by observing the long-term consequences of actions in each state. The short-term consequences is easy to calculate. That's just the reward. Although performing an action yields an immediate reward, it's not always a good idea to greedily choose the action with the best reward. That's a lesson in life too, because the most immediate best thing to do might not always be the most satisfying in the long run. The best possible policy is called the optimal policy, and it is often the holy grail of RL as shown in this figure, which shows the optimal action given any state. The long-term reward is called a utility. It turns out that if we know the utility of performing an action at a state, then it's easy to solve reinforcement learning. For example, to decide which action to take, we simply select the action that produces the highest utility. However, uncovering these utility values is the harder part to be sorted out. The utility of performing an action A at a state S is written as function Q of S, A called the utility function that predicts the expected immediate reward, plus rewards following an optimal policy gave the state action input as shown in the diagram. Most reinforcement learning algorithms boil down to just 3 main steps that infer, do, and learn. During the first step, the algorithm selects the best action A given a state S using the knowledge it has so far. Next, it does the action to find out the reward R as well as the next state S dash. Then, it improves its understanding of the world using the newly acquired knowledge.